Greetings, class. In the previous weeks, we focused on testing whether means are significantly different between groups or from a given value. For example, we could compare whether boys and girls have different verbal communication scores. In the next couple of weeks, we'll move from comparison of means to the association between variables. For example, we might examine whether students' SAT scores are related to their college GPA. So be clear that we are now examining association, not comparison. In statistics, we often want to know whether and how two variables are related. There are a variety of measures of bivariate relationships. They differ in two aspects. First, what type of variables are involved, and second, what kind of relationship is expected. Is it linear or nonlinear? All measures of bivariate relationships provide information about how strongly two variables are associated. They all focus on two key characteristics of correlation. One is the direction of the relationship, which can be positive, negative, or curvilinear. The other is strength, which refers to the magnitude of the association between the two variables. The focus of this video is a detailed discussion of the Pearson product moment correlation coefficient, or Pearson correlation R. The Pearson's R is the most frequently used measure of the relationship between two variables. Knowledge of this relationship helps us determine how one variable changes concerning the other. Pearson correlation coefficient measures the strength of association between two quantitative variables measured from the same sample that have a linear relationship. In other words, both variables x and y must be either interval or ratio variables. The best way to verify whether they share a linear relationship is to create a scatter plot. If you're unsure how to generate a scatter plot, refer to the video tutorial linked to this slide. Let me use a simple example to explain the Pearson correlation coefficient R. A random sample of 10 kindergarten students completed a vocabulary test at the beginning and end of a week. Their scores on the two tests were examined for correlation. The two variables, test A scores and test B scores, are both continuous measures taken from the same group of students. A scatter plot shows that there is a linear relationship between the two variables, with one outlier. Be clear that in the scatter plot, each point represents paired measures on the two variables for a specific individual. Conceptually, based on Sir Karl Pearson's formula, the product moment correlation coefficient is the mean of the cross product of the standard scores of two variables. The calculation takes a few steps. First, standardize both variables so that the raw scores are converted into z-scores. For each individual, multiply the two z-scores to find the cross product. Then, calculate the sum of those cross products for all individuals in the sample and divide it by the degrees freedom n-1. In my example, the test A scores have a mean of 5.6 and a standard deviation of 2.22. A raw score of 9 is converted to a z-value by subtracting the mean 5.6 and dividing the difference by the standard deviation 2.22, which gives 1.53. The test B scores have a mean of 7 and a standard deviation of 4.35. A raw score of 10 is converted to a z-value by subtracting the mean 7 and dividing the difference by 4.35, which gives 0.69. The product of the two z-scores is 1.53 times 0.69 equals 1.06. If we do the same for everyone in the sample, the sum of the cross products is 5.28. Dividing it by the degrees freedom, 10 minus 1 equals 9. The Pearson R is 0.59. The conceptual formula can be transformed into two different routes for calculating the Pearson correlation: the deviation score formula and the raw score formula. Since it takes only a couple of clicks to get the value in SPSS, I will skip the calculation details. What's important for you to know is that the correlation coefficient R is a quantitative index that describes the extent to which two variables are related. That is, the correlation is a statistic that numerically describes the general tendency of the degree of association between the two variables. Pearson's R provides a measure of association between two continuous variables by defining both the strength of association and the direction of the relationship. Pearson's R is always in the range of -1 to +1. The absolute value of R indicates the strength of the relationship, that is, how strongly two variables are associated. When R is close to 0, the relationship is weak or non-existent. The closer the absolute value of R is to 1, the stronger the correlation. So if you are given two Pearson's R values, R1 equals -0.85 and R2 equals 0.77, can you tell which one indicates a stronger relationship between the two variables? The positive or negative sign of Pearson's R values indicates the direction of the relationship. A positive relationship indicates that the values of the two variables move in the same direction. When x increases, y increases. When x decreases, y decreases. A negative relationship indicates that the values of the two variables move in opposite directions. As the scores of x go up, the scores of y go down, and vice versa. For example, a negative correlation between time spent outdoors and depression levels means that more outdoor hours are associated with lower depression. One key property of correlation is that it is symmetric, meaning that the correlation between x and y is the same as between y and x. On this slide, I have a few examples to show how different relationships appear visually in scatter plots. The two scatter plots at the upper corners show perfect relationships because all points lie on a straight line. The one at the center bottom indicates a very weak or non-existent relationship, and the R value is close to 0. All the scatter plots together demonstrate that the closer data points cluster around a straight line, the stronger the bivariate relationship. Pearson's R is an ordinal scale. Therefore, deciding what magnitude of R indicates a noteworthy relationship is somewhat arbitrary and depends on contextual factors. Two variables with R equals 0.6 does not necessarily have a relationship twice as strong as another two variables with R equals 0.3. As a rule of thumb, when the absolute value of R is between 0 and 0.2, it indicates a weak relationship. when the absolute R value is between 0.2 and 0.6, it indicates a moderate correlation. When the absolute R value is above 0.6, it indicates a strong correlation. However, this is just a rule of thumb. The specific variables and the nature of their association determine whether a correlation should be considered weak, moderate, or strong. Several factors may affect the estimate of R values. First is the linearity. If you use Pearson's R to measure a curvilinear relationship, you will underestimate the relationship and produce misleading results. Second is truncated range. If the range of the variables is restricted, the absolute value of R will decrease and be underestimated. For example, if we collect data from all students admitted to a university whose high school GPAs range from 2.0 to 4.0, the correlation between high school GPA and college GPA might be R equals 0.70, indicating a strong positive relationship. However, if we only look at honor students whose high school GPAs range from 3.7 to 4, because there is much less variation in high school GPA, the correlation drops to 0.3. The third factor is sample size. A large sample size produces a more accurate estimate of Pearson's R. But if the range of the variables is not affected by sample size, the sample size has little impact on the value of R. Pearson's R is a type of correlation coefficient. Correlation coefficients allow us to determine whether, on average, the values on one variable are associated with the values on the second variable. However, do not confuse correlation with causation. Correlation simply means that variation in the scores on one variable corresponds with variations in the scores on the second variable. Causation, on the other hand, means that variation in one variable causes or creates variation in the other. While causation implies correlation, correlation does not imply causation. If we measure the correlation between two variables from a sample, we need to verify whether the correlation R indeed indicates a real relationship in the population, or if it happened by random chance. Here, the tool we use is the one-sample test of Pearson correlation coefficient. The null hypothesis H0 is rho equals 0, stating that there is no relationship between the two variables in the population. The alternative hypothesis HA is rho does not equal 0, indicating that the correlation between the two variables in the population is significantly different from 0. Here, rho represents the population parameter of R. When rho equals 0, the sampling distribution of the correlation coefficient follows a t-distribution with n-2 as a degrees freedom. The formula to calculate the observed t-statistic is R times the square root of sample size minus 2 over 1 minus R squared, in which R is the correlation in the sample and n is the sample size. Compare the observed t-value with the critical t-value, or compares p with alpha to decide whether to reject the null hypothesis. If the null is rejected, we conclude that there is a relationship between the variables in the population. But this does not imply anything about the magnitude of the relationship, only that it is different from 0. It's not easy to construct a confidence interval for R because the sampling distribution of R is not normal when rho does not equal 0. This means we cannot use Z or T distributions directly to estimate confidence intervals. Sir Ronald Fisher developed a solution called Fisher's Z transformation, which converts R values into Z-scores. The transformation is complex, but you can use a table provided in the textbook appendix or an online converter. Once converted, the standard error of the Z distribution is 1 over the square root of n minus 3. The confidence interval in Z form is the Z-score converted from R plus minus the standard error of the converted Z distribution times 1.96. Another concept related to Pearson's R is the coefficient of determination, R squared. When two variables are correlated, they share a certain percentage of variance, meaning some of the variance in one variable can be explained by the other. The square of the correlation coefficient provides a quantitative measure of the proportion of total variance in one variable that can be associated with variance in the second variable. In other words, it tells how much of the variance in Y can be explained by X. In the kindergarten vocabulary example, R equals 0.59. To test whether it's significantly different from 0, I used alpha equals 0.10, given the small sample size n equals 10. The critical t-value with degrees freedom 8 and alpha 0.10 is plus minus 1.86. The observed t is 2.067, which is greater than the critical t-value. So we reject the null hypothesis and conclude that there is a significant relationship between the two sets of test scores. The coefficient of determination is R squared equals 0.348, indicating about 35% shared variance between the two sets of scores. To construct the 90% confidence interval, we convert R equals 0.59 to a Z-score 0.678. The standard error of the Z distribution is 1 over the square root of 10 minus 3, which is 0.378. Given alpha equals 0.010, the Z critical value is 1.645. So the confidence interval is 0.678 plus minus 0.378 times 1.645. The range is from 0.056 to 1.3 in Z-scores. Converting the Z-scores back to R values gives an interval from 0.051 to 0.86. Although not often seen, we can test whether two correlation coefficients are significantly different. Similar to constructing the confidence interval, the two R values need to be converted to Z-scores for the test of rho 1 equals rho 2. The key is to calculate the observed Z value using this formula. The other steps are similar to other hypothesis tests. To obtain the Pearson correlation coefficient R in SPSS, open the data file, go to Analyze, Correlate, Bivariate, and bring the pair of variables to the right window. Click the Options button to request the mean and standard deviation information. Click Confidence Interval to specify the desired level of significance. When ready, click OK. The output provides 3 tables. First table is the descriptive statistics for the 2 variables. Pearson correlation R and p-value for the test of rho equals 0 are provided in the second table. R, P, and confidence interval are in the third table. Since P equals 0.74 is less than alpha equals 0.10, we conclude that R equals 0.59 is significantly different from 0. In the last part of the video, I will briefly introduce a couple of other measures of bivariate association. One is Spearman's rho. The Spearman's rho is a specialized form of Pearson's R that is appropriate for ranked values. In other words, it measures relationships between ordinal variables. I've provided the formula for Spearman's rho here for your reference. You can easily obtain Spearman's rho in SPSS. Its value is also between -1 and +1, and the interpretation is the same as for Pearson's R. Keep in mind that both Pearson's R and Spearman's rho require a linear relationship between the 2 variables. The only difference is that Pearson's R is used for continuous variables, where Spearman's rho is used for ordinal variables. Covariance is another term you will often hear. The covariance of x and y is another way of expressing the relationship between 2 continuous variables. For both variables, the deviation scores are calculated as the difference between the raw score and the mean. For each individual, multiply the 2 deviation scores to find the cross product. Then, calculate the sum of those cross products for all individuals in the sample and divide it by the degrees of freedom n-1. The covariance is calculated without standardizing the variables, so its size depends on the units of measurement of the 2 variables. Unlike Pearson's R, it's not bounded by -1 to +1. Correlation and covariance are mathematically related. Pearson's R can be found by dividing the covariance by the product of the standard deviations of x and y. Correlation is useful because a strong association between 2 variables, x and y, allows us to predict y based on the information we know about x. This is especially valuable when information about one of the variables is difficult to obtain. For example, students' success in college can be predicted by their scores on academic aptitude tests such as the SAT or ACT. In order to make such predictions based on correlation, we need to take it a step further into regression analysis, which will be the topic of next lesson.